Hey, welcome to example 2, where we're going to find the integral of the function 8x dx here from 1 to 4. So one way to do this is to use a rule that allows us to move constant multipliers in front of the integral. So the rule in the dotted line here box says that if I have some function multiplied by a constant k, then I can move the constant out front of the integral symbol. So in this example over here, I have the function just x multiplied by the value k equals 8. So I can move that 8 in front of the integral and just focus on taking the integral of x dx. What we want to notice here is x is the same thing as x to the 1. So it looks a lot like the function we talked about in the previous video for functions that look like x to the n. So we're going to use that rule, the power rule, for antiderivatives to find the integral of this function. So I'm going to move the 8 out front and then just focus on the function x, or x to the 1. The rule from the last slide in the last video said that the integral of x to the power of n was equal to x to the power of n plus 1, so raise the power by 1, and then divide by that new power, n plus 1. And then add a constant on the end to take into account the fact that there are many antiderivatives for the function x. So in this example, because it's x to the 1, we're going to raise the power to the number 2. So we have x to the power of 2, and then we have to divide by that original power, the new power, which is also 2. Then we add plus c, and then we have to evaluate that from 1 to 4. So that's what the fundamental theorem of calculus tells us. It says the integral of a function from a to b is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. The antiderivative of our function x, our big F in this case, is x squared over 2. That's the antiderivative, because if I take the derivative of x squared over 2, I'm going to get back the original function x. So the fundamental theorem of calculus says to insert the higher limit of integration into the antiderivative. So I'll start by putting 4 into this function. I'm going to leave the 8 out here for the very end. So I have 4 squared over 2, which is here, plus c, and then minus, because the fundamental theorem of calculus says always to subtract these things, and then I evaluate the antiderivative at 1. So now I have 1 squared over 2 plus c. Now I have a little bit of careful arithmetic to do here. So our next step is going to look like this. I have 4 squared is 16 over 2 plus c minus 1 squared is 1 over 2 plus c. Now this minus sign right here has to be distributed into both terms of this set of parentheses right here. So what I get is 16 over 2 is 8 plus c. I remove those parentheses since they're no longer needed. And then minus 1/2 is right here. And then minus a positive c gives me a negative c. Now what I want you to notice here is that I have positive c and negative c. And so the c's go away, so to speak. And we really don't actually need them way up here in this second line, because the fundamental theorem of calculus says always subtract these two things. And so if I start with a c and then I subtract a c from it, I'm always going to end up with 0. So we did it this one time, but it turns out moving forward that when we find the antiderivative of a function, we don't really have to write this, because they basically take care of themselves way down here in this step. So this positive c and this negative c are 0, and so I end up with the 8 on the outside, and then 8 minus a half is 7.5. And then when I multiply the 8 by the 7.5, I get 60. So that is my final result. Now remember, this represents a signed area. So if I were to take a look at the picture of this function, this is a straight line, y equals 8x. And if I look at the area trapped between 1 and 4, between the graph and the x-axis, this area would be exactly equal to 60. That is the signed area. Now in this case, there was no negative area that the integral would have subtracted. It's all positive, but the integral makes sure to take that into account. There's one more thing that I would like to mention here, and that is way back up here when we were finding the antiderivative, if we had not removed the constant 8 out in front, we would still be okay, because notice this. What is an antiderivative of 8x? In other words, give me a function whose derivative is equal to 8x. Well, if we were to take this expression here and then raise the power in the x to a 2, we would end up with 8 times x squared. Then we would have to divide by the new power. So we would have 8 times x squared over 2, but 8 over 2 is 4. So this expression right here, 4x squared, is an antiderivative of 8x, because the derivative of 4x squared is what? It's 8x. So if we had recognized this from the beginning, we could have just used this as our antiderivative, plugged 4 into 4x squared, plugged 1 into 4x squared, and subtract them. When we do that, we would have gotten the same exact answer that we got down here, which is 60. So you might want to try this on your own to see and to make sure that you would get 60 if you evaluated this antiderivative at 4 and 1 and then subtracted them. You should get 60, but it's a good exercise for you to try on your own. So that's example 2. The next video we'll move on.